So recall when we were doing second order equations and we had repeated roots, in order to get second solution, we'll call y1 the first solution. To get the second solution, we multiplied that solution by t, right, to create this second linearly independent solution. And in systems of differential equations, we're going to do something similar. If we have one solution, let's say C1 e to the lambda t x1, where x1 is the eigenvector for lambda, but lambda is repeated and we don't get a second eigenvector. Sometimes you can get two eigenvectors out of one eigenvalue, but if you don't and you only get one, how do we get that second solution? So it turns out that the second solution, we'll call this y1, this will be y2. The second solution is going to be kind of similar to what we did for second order. We're going to call it C2, say with a constant, and then times this big vector. We're going to have that t, e to the lambda t x1. So that's going to be this same eigenvalue, eigenvector solution plus e to the lambda t x2, and x2 has to be solved for. So how do we get x2? We're going to say solve this equation to get x2. A minus lambda I x2 set equal to x1. So you're actually going to put this eigenvector that you found into the right side of this equation, solve for x2, and you're going to put x2 here, and this whole thing is going to be your second solution. So it's kind of weird and convoluted, but once you get the hang of it, it's not too bad. You just got to do one extra thing, get this second vector and this second vector and plug it in, and you get your solution. So let's do an example. We have this system. I need to find the eigenvalues, so let's do this up here. Determinant of 2 minus lambda 1, negative 1, 4 minus lambda. So that's 2 minus lambda times 4 minus lambda plus 1. So what is that? We get 8 minus 2 lambda minus 4 lambda plus lambda squared plus 1. And rewrite this. It's lambda squared minus 6 lambda plus 9. And you can see this is a perfect square, right? So this is lambda minus 3 squared. So we get lambda equals 3 with multiplicity equal to 2. It's a double eigenvalue. So we need to find the eigenvector that goes with this eigenvalue. So we're going to solve a minus 3i x1, set it equal to 0. So I'm going to subtract 3 from the main diagonal. So that's going to give me negative 1, negative 1, 1, 1. And you can see that that's going to reduce pretty easily to 1, 1, 0, 0, 0, 0. So we have leading 1. This is a free variable. Let's call this A and B. So A is equal to negative B. B is free. So let's make B 1. So our eigenvector 1 is going to be negative 1, 1. So we did not get two linearly independent eigenvectors out of this one eigenvalue, but we need two to get, our second solution, and so we can span our solution set, get a fundamental set. So now we're going to solve a minus 3i x2, right? We're going to solve for x2, but now we're going to set it equal to x1. So we're just going to put this, my pen messed up. Now we're going to put this x1 in here and solve that system, see what we get. Right, so that's a minus 3i. And now I'm going to augment with -1, 1. You see this is going to reduce to 1, 1, 1, 0, 0, 0. Again, let's call this A and B. So A is equal to 1 minus B, and B is free. Let's let B be equal to 1 again. So this x2 vector is going to be 1 on the bottom and 0 in the first component. So that's x2. So let's go back to our solution. Y2 is going to be this whole thing, right? So we need x1 and x2 here. So I'm going to write that as our second solution. Well, let's just write the whole thing. We've got y equals, first solution is c1 e to the 3t times -1, 1. And then c2 times t e to the 3t -1, 1. So that's t e to the lambda t, and this is x1, plus e to the lambda t times x2. And that whole thing is your pair of solutions put together.